Hi everyone, today I will be presenting my Physics 102 final term project. In this project I will be investigating the relationship between the input and output voltages and the number of wire wraps and conservation of power in a simple transformer. And I built this transformer using steel nuts and copper made wires. So let's look at the equipment and details. My objective of this experiment is to build a simple transformer using nuts as the core and investigate the relationship between the input and output voltages and the number of wire wraps in the first and second coils, power input and output. The experiment will demonstrate the principles of electromagnetic induction and transformer efficiency. This is the main setup of the experiment, which consists of a steel nut and some number of copper wires wrapped around it. And this is an oscilloscope, which is used to observe the waveforms of the voltage and record the input and output voltage of the primary and secondary coils. And this is a multimeter, which is used to measure the current in the primary and secondary coils of the transformer. And finally, an AC waveform generator to create current and also AC voltage. In the first stage of the experiment, the features of the step-up transformer is tried to be observed. At each data point, 1 ampere current is provided for the primary coil and the output current is measured from the secondary coil. In stage 1 data point 1, primary coil's number of turns was 30 and the secondary coil's number of turns was 15. The input voltage is measured as 5.45 volt and the output voltage is measured as 0.1870 volt. The current was 0.07 ampere. In stage 1 data point 2, primary coil's number of turns was 60 and the secondary coil's number of turns was 20. The input voltage is measured as 4.7 volt and output voltage is measured as 0.1870 volt. The current was 0.05 ampere. In the stage 1 data point 3, primary coil's number of turns was 60 and the secondary coil's number of turns was 15. The input voltage is measured as 4.45 voltage and the output voltage is measured as 0.1870 voltage. The current was 0.06 ampere. In stage 1 data point 4, primary coil's number of turns was 60 and secondary coil's number of turns was 10. The input voltage is measured as 6.05 volt and the output voltage is measured as 0.1870 volt. The current was 0.07 ampere. And to make a step-down transformer in stage 2, I basically used the other side of the transformer as primary coil, which has lower number of turns on it. In the second stage of this experiment, the features of the step-down transformer is tried to be observed. At each data point, 1 ampere current is provided again for the primary coil, and the output current is measured from the secondary coil. In stage 2 data point 1, primary coil's number of turns was 10, and secondary coil's number of turns was 60. The input voltage is measured as 4.25 volt, and the output voltage is measured as 0.1145 volt. The current was 0.07 ampere. In stage 2 data point 2, primary coil's number of turns was 15 and the secondary coil's number of turns was 60. The input voltage is measured as 8.45 volt and the output voltage is measured as 0.1750 volt. The current was 0.05 ampere. In stage 2 data point 3, primary coil's number of turns was 20 and secondary coil's number of turns was 60. The input voltage is measured as 8.55 volt and the output voltage is measured as 0.1570 volt. The current was 0.06 ampere. In stage 2 data point 4, primary coil's number of turns was 15 and secondary coil number of turns was 30. The input voltage is measured as 5.70 volt and the output voltage is measured as 0.1125 volt. The current was 0.07 ampere. This is the formula I used to calculate the error rate. Since the relation between the input and output voltages and the number of wire wraps is investigated, the error rate will be measured by taking the secondary coil's number of turns over primary coil's number of turns as the theoretical value, and the secondary coil's voltage over primary coil's voltage as experimental value. And this is the formula I used to calculate the power efficiency of the system. In the formula, basically the output power and the input power are divided and multiplied with the 100%. And these are the data tables. In this experiment, the results showed significant errors between the theoretical and experimental values for both step-up and step-down transformer stages. In stage 1, although an oscilloscope was used to get more detailed voltage measurements, the error rates were still extremely high, ranging from several hundred%. This was mainly because the secondary voltages were very low, which was around 0.13 and 0.20 volts, and this made the measurements sensitive to any small losses or noise. Factors such as flux leakage from the steel nut core, high resistance in the wire coils, and the loose winding construction contributed heavily to the inaccuracy. Additionally, the oscilloscope displayed waveforms, distortions, and phase shifts, which further affected the output readings. And in stage 2, the errors became even larger, reaching up to tens thousands of percent error rates. The output voltage dropped even more, and the effects of stray capacitance, core nonlinearity, and parasitic losses became dominant. These issues caused major deviations from the expected turns-radio relationships. Even though measurements precision improved by using an oscilloscope, the physical limitations of the setup, especially poor magnetic coupling and resistive losses, were the main sources of error throughout the experiment. The plot of voltage in over voltage out versus number of turns in over number of turns out in stage 1 shows that the experimental voltage ratios are much higher than the theoretical turn ratios. Ideally, the points should align along a straight line with a slope close to 1, meaning that the voltage ratio directly matches the turn ratio. However, in the experiment, the data points are scattered from this ideal line. This large deviation is mainly due to flux leakage from the steel nut core, resistance in the coils, and the measurement noise at very low output voltage. As a result, the transformer in this stage could not maintain the expected relationship between the number of turns and the voltage ratio. In stage 1, plot 2, the plot of input power in versus output power out in stage 1 reveals that almost all input power was lost and very little was transferred to the output. The data points lie very far from the ideal line, where power in equals power out. This result shows that the transformer was extremely inefficient, with efficiency values below 1%. The main causes of the poor performance were energy losses due to resistance in the wires, poor magnetic coupling, and the leakage of the magnetic field. Although the oscilloscope allowed a better voltage measurement, the physical construction of the transformer limited the energy transfer. And in stage 2, plot 1, the voltage in and over voltage out versus number of turns in over number of turns out plot shows even larger error compared to stage 1. The output voltages were even lower, making the system more sensitive to disturbances such as stray capacitance and core nonlinearity. As a result, the experimental voltage ratios deviated greatly from the theoretical turn ratios, with error reaching thousands of percent. The plot clearly showed that the simple transformer model did not hold under these conditions, mainly because the poor quality nut core and the coil winding imperfections made it impossible to achieve the expected behavior. And in stage 2 plot 2, the power in versus power out plot for stage 2 confirms that the transformer was extremely inefficient. The output powers were almost negligible compared to the input powers. Similar to stage 1, the points are located far from the ideal line, where power in would equal power out. The energy losses were mainly caused by the poor magnetic properties of the core, significant flux leakage, and additional parasitic effects at very low output voltage. Even though the measurements were made carefully using an oscilloscope, the transformer design itself was not suitable for efficient energy transfer, leading to very low power efficiencies. Overall, the experiment showed that the output voltage depends on the coil turns ratio, as predicted by the Faraday's law. but the measured results were far from ideal. Using an oscilloscope helped to capture better details like the waveform shape and phase, yet the experiment's efficiency remained very low, with the most power lost instead of transferred. The steel not used as the core had poor magnetic properties, causing heavy flux leakage and very low output voltage. The loosely wound coils and the parasitic effects like stray capacitance and the core non-linearity also had a major impact on the results. Despite the large errors, the experiment still confirmed that the basic principle that changing magnetic flux induces voltage. To improve the results in future experiments, a proper transform core made of ferrite and or laminated iron should be used, and the coils should be wound more tightly and evenly. Increasing the number of turns would also help to achieve higher output voltages and reduce measurement errors.